If I have a bar magnet that is oriented such that the North Pole is above the South Pole, and I bring it close to another bar magnet, which is oriented in the opposite direction, so the South Pole's on top, the North Pole's on the bottom. When I bring them close to each other, the North Pole will be attracted to the South Pole, and the South Pole will be attracted to the North Pole, and these two magnets will attract one another. If I were to take one of those magnets and then flip it such that the two magnets were oriented in the same direction, maybe with the North Pole on the top, South Pole on the bottom, and the North Pole on the top, South Pole on the bottom, and I bring those two magnets close to one another, the North Pole would be near the North Pole and the South Pole would be near the South Pole. And when we have like poles, we know that similar to charges, that those poles will repel one another. And up above, when we had opposite poles, we know that they attract. This is very similar to what we found when we studied charges. If I have two opposite charges, a positive charge and a negative charge, we know that those two charges will attract one another. And if I have two like charges, whether it be positive and positive or negative and negative, when I bring these charges next to one another, they will repel. So previously we had the law of charges, which said that like charges repel and opposite charges attract, and now we have the law of poles, which says that opposite poles, north and south, attract one another, and like poles, north and north or south and south, repel one another. So charges and magnets can be quite similar. There are a lot of similarities between charges and magnets, electric fields and magnetic fields, but there are also some key differences. They're not the same. For example, if I wanted to isolate a charge, if I wanted to just have an isolated negative charge or an isolated positive charge, that is something that I can accomplish. I can have just a single proton or a single electron. I can separate the positive charge from the negative charge quite easily. But if you try to do the same thing with a bar magnet, for example, if I were to cut the bar magnet in half, then what you will find is that the top piece will have a north and a south pole, and the bottom piece will also have a north and a south pole. And if we were to cut that again, we would find the same thing, that one piece would have would generate two pieces when it gets cut in half, and each of those two pieces would have a north and a south pole. So I can separate charges, but I can't separate the two poles of the magnet. What we know so far is that no matter how many times we subdivide a magnet, or no matter what we do, we should end up with two poles, both a north and a south pole. We know that not all materials are magnetic, but if you take a piece of material that is magnetic and you place it somewhere near the Earth, let's say we hang the magnet from a string, then we would find that the magnet tends to align itself in the same direction. If we place the magnet in the same place at different times or in different orientations, it will tend to twist and turn and align itself such that maybe the north end of the magnet is in one place and the south end of the magnet is in the other place. So if I were to draw the Earth relative to this magnet, then it might be something like this, where maybe the axis of the Earth, the axis that it rotates around, is there. And so the Earth is rotating around. There is a magnetic field which is generated inside the core of the Earth, and that magnetic field exists everywhere around the Earth. What we typically call the North Pole is what I'm drawing here. And the North Pole is there, and the North Pole of the magnet that I've drawn is here. And what it looks like is the magnet which I've hung from this string, the north end of that magnet is attracted to the North Pole of the Earth. But what I showed previously is that if I have like poles, north and north, that those things repel one another. And so what is the problem? This north pole which I've drawn, we're now going to refer to as the geographic north pole. Because the geographic north pole is actually the south pole of Earth's magnetic field. So I'm going to draw a little bar magnet that exists on the Earth, where the south pole of that magnetic field which exists around the Earth is at the geographic north pole, and the north pole of that magnet, or the north end of the magnetic field, is on the south geographic pole. And so the magnetic field and the geographic poles are, oppositely aligned. They don't have anything to do with one another. The magnetic field is what it is. It's the way it's generated, and by convention, then we can name other magnets the north or south pole. The geographic north pole is a decision that is made, and it just so happens to be that currently the geographic north pole and the magnetic poles do not align in terms of the names. So if I take a magnet and one end of it happens to point toward the geographic north pole, which is the southern pole of the magnetic field, then I know that that end is what we call the north end of the magnet. And so without diving too much into how the material becomes magnetized or why it's magnetized, we can at least know that if I have a material and it aligns itself in Earth's magnetic field such that the north end points towards the geographic north pole or the magnetic south pole, then we know that that's the north end of the magnet, and that's how we'll define the two poles of any magnet. Now we're going to look at the magnetic field around the Earth to understand a little bit how magnetic fields are drawn and a little bit about how the Earth's magnetic field looks. If I have a picture of the Earth, somewhere there's a north geographic pole. So I'm going to write north pole. And somewhere, on the other side of the planet, then there's the south pole. And the north and south pole are not necessarily aligned with the poles of the magnetic field. Not even just that they're flipped from one another, but the magnetic field is tilted a little bit away from the geographic north and south poles. And so here I'm going to draw at an angle maybe about 10 degrees away from the north pole and south pole are the south and north poles of the magnetic field, which I'll just label N and S. So magnetic field lines, which are lines of force, they show the direction that charged particles would feel a force. They don't actually exist. We can't see them, but we know that they exist due to the influence that they have on particles. And so what would the magnetic field around the Earth look like? What we would find if we took a compass and were able to, navigate all around Earth and see which way the compass pointed, then we would find that the compass would lead us to draw electric field lines which all start at the north end of the magnetic field of the Earth, and they all go through the south end of the Earth's magnetic field. So something like this, where they start at the north end and go around the Earth and come through the south end. And they have a direction to them. They would go in this direction. And we could draw another line going in the opposite direction. And these lines always point from the North Pole to the South Pole. And so we could draw lines forever, but this gives us a little bit of an idea as to what the magnetic field around the Earth looks like. A couple key differences between magnetic fields and electric fields, because you might start to think that this looks incredibly similar to the electric field that we have mapped previously when we had different charged components in a circuit. And it does look very similar, and the lines represent similar things. They are lines of force. But one key difference between magnetic field lines and electric field lines is that a magnetic field line doesn't start and stop somewhere. For an electric field, if I were to draw a positive charge and a negative charge, and I drew electric field lines, those lines represent the force that a positive charge would feel, which means they need to go from positive to negative, something like this. Which means all of those electric field lines started on a positive charge and ended on a negative charge, something like that. So the phrase is that it starts on the positive charge and ends on the negative charge is key. Where when I'm dealing with magnetic field lines, they don't start on the North Pole, end on the North Pole. I drew them as starting on the North Pole and ending on the South Pole, but they go through the two poles. So they're a closed loop. They don't start and end in any particular place. They are closed loops that run between the two poles. So those lines do appear to begin at the North Pole and end at the South Pole. But even if we have a bar magnet which has a North Pole and a South Pole, and we consider drawing some magnetic field lines around that magnet, then everywhere we could start our magnetic field lines at the North Pole and then go toward the South Pole, but those magnetic field lines are still loops which would go through the magnet itself, something like this. And you can imagine other lines which run closer to or further away from the magnet. The magnetic field which we've just been talking about is defined by the following thing. The magnetic field which we will use the capital letter B for, which is a vector. So we use the capital letter E for electric field, a lowercase letter G for a gravitational field, and a capital letter B for magnetic field. The magnetic field is defined by the fact that moving charges can experience a magnetic force. And for magnetic force, we'll use F subscript B. Okay? So if you have a charge which is moving in a magnetic field, then it experiences a force. The force that it feels, FB, is given by Q times V times B times sine of theta. Anytime we've had theta in an equation like this, theta usually represents the angle between two vectors. And force is a vector, and so there must be two things on the right-hand side of the equation which are vectors. The two things are either Q, V, or B. Earlier, I already said that the magnetic field B is a vector, and the other thing that's a vector is V. V represents the velocity of the charged particle, Q represents the charge of that particle, and B represents the strength of the magnetic field, and the angle theta is the angle between V and B. And so this equation tells us the equation for the magnetic force that a charged particle would feel moving through a magnetic field. We know already that Q stands for charge, which is measured in coulombs. We know that V stands for velocity, and it is measured in meters per second. We know that theta does not have any units. It's measured in degrees or radians, but in our equations does not contribute a unit to the other side of the equation. We know that that F stands for force, and it's measured in newtons. But we don't yet know what the units of B are. What are the units of magnetic field? So let's rearrange the equation for B. B equals F divided by QV sine theta. And I know that B will have the units of the stuff that's on the right-hand side. So on the right-hand side, F has units of newtons. Q has units of coulombs. and V has units of meters per second. And if I rearrange this a little bit, then what I see is that this would be newtons divided by coulombs per second times meters. A coulomb per second is charge per unit time. So if we think about this, charge per unit time is current, and current is measured in amps. And so this equation, the units of this equation could also be written as newtons divided by amps times meters. And a newton per amp meter is, by definition, a Tesla, T-E-S-L-A, or if you have multiple Teslas, which can be abbreviated with a capital letter T. And so the units of, or I guess 1 unit of magnetic field is Teslas, which is abbreviated with a capital letter T. While we won't dive into any examples right now, we should be able to see, based off of what we've talked about with the magnetic field and now magnetic force equation, is that if I have a charged particle, has a certain charge Q, and it's moving through a magnetic field, which we know can have various directions depending on where we are in the magnetic field. Maybe the magnetic field direction points this way, and maybe the velocity of that particle is oriented in this direction, and there's an angle between those two vectors. The force that that particle will feel depends on what the velocity is, the magnitude of that magnetic field, and the angle between those two vectors, and also the charge itself. If I know all of those things, then I can determine the force and therefore the acceleration and therefore the kinematics, the motion of that charged particle as it moves through a magnetic field. The last thing I'd like to point out is that while force, velocity, and magnetic field are all vectors, in this equation, similar to a few equations that we've seen in the past, in this equation we will use the magnitude of all of these quantities. So the magnitude of the charge, the magnitude of the velocity, and the magnitude of the angle, which I'm going to kind of abbreviate by just drawing a couple of absolute value bar signs there. Which gives us the magnitude of the force. And so this is an equation which is going to give us the magnitude of the force experienced on the charge. The direction is something that we'll come back and learn how to do later.